Hello, in this video, let's talk about wires. So various blocks in the chip are connected using wires. In chips, these are known as interconnects. Now, as transistors switch faster because of dimensional scaling, the performance of chips is increasingly dominated by the interconnect. And how so? The wire resistance contributes to additional delay. On-chip interconnect inductance also limits systems, especially when we are talking about high-frequency systems. And capacitive coupling between the wires also introduces sources of error in the interconnects. So let's look at some of these effects in detail in this video. So here's a cross-section of what a typical metal stack looks like. So wires allow you to connect transistors. And if you look at modern technologies, we typically have between 12 to 15 layers of metal which are available for creating interconnections. And typically the lower level metals are allowed to run only in a particular direction, and that is because of the fact that these are very tightly packed layers and lithography and etching constraints will not allow you to allow for jogs, etc. And also what you see is as you go higher and higher up on the metal stack, the metals widen and you can draw longer lines. So you see that the resistance of the metal lines keeps reducing as you go higher and higher up the metal stack. Now, what do these interconnects do? They lead to an increase in the propagation delay. They also impact energy dissipation in the chip, and they introduce new noise sources and to a large extent impact the reliability of the chip. And normally modeling of these interconnects is dauntingly complex. It's not something which is very simple to do. And as technologies scale and as these stacks become more and more complicated, it becomes harder and harder to do complete simulations. So let's talk about these effects in detail. Let's first begin with a capacitance. So if you think about if you think about an interconnect is nothing but a conductor that is embedded in a dielectric with other conductors around it, right? So now let's consider a line which has a width of W, a height of H and a length of L that is into the screen of the video. Now if you assume that this W is much larger than H, then if you look at the field lines between this metal line and a metal or a substrate that lies below, we can model this approximately as a parallel plate capacitor with the interconnect capacitance given by the dielectric constant of the dielectric in which the interconnects are embedded divided by the thickness between the two interconnect layers times the cross-sectional area. Now in real interconnect lines, what happens is the wires are as tall as they are wide, and in some cases they're actually taller than they're wider. So this kind of a model falls insufficient when you want to do modeling of capacitance. So generally a lot of the capacitance of the wire comes from the fringing fields that come from these vertical plates that are present in the interconnect. And so another quick model, if you were to just treat this as a circular wire with a diameter h, that is, then you can model it essentially as a capacitance using basic Maxwell's equations. Now in generic case, what happens is so if you think about the capacitance of the wire, it depends on what is the wire adjacent to it or how close they are to each other. It also depends on what is the thickness of dielectric between this layer and the layer prior to it and this layer and the layer after it. So in general, this is a very complicated structure to model and extract the capacitance. So typically we model all this using a capacitance per unit length metric. Right? So every layer in your PDK is going to have a C per unit length that is used for modeling the capacitance of the interconnects. Similarly, when you talk about the resistance of this metal line, the resistance, again, this is a conductor carrying electricity. So the resistance is simply given by rho L upon A, and in which case is given by rho L divided by W times H, the cross section of current conduction. So remember, current is flowing into or out of the screen. In other words, I can write this as a parameter sheet rho, that is rho SH, which is nothing but the sheet resistance of the layer, into length divided by W. So again, what you see is that the resistance of this wire is going to increase as you make the wire longer, and it's going to reduce as you make the wire wider. So in most current technologies, copper is the metal of choice for interconnects, and that is primarily because it provides an ideal mix of low resistance and immunity to electromigration. But what happens is that copper requires a liner before the copper is electroplated onto the metal trench. And as the dimensions of these lines scale, what happens is large part of the cross section of the interconnect is dominated by this high resistance liner. And so what happens is that as you scale the dimension of the interconnect, in addition to the cross-sectional area reducing, because a large part of the cross-section is also dominated by the high resistance, the resistance of the wire keeps increasing. Now, copper at very high current densities suffers from electromigration. Electromigration is a process by which, because of the high currents that are flowing in the line, they actually transfer some momentum to the molecules of copper in the lattice, causing the molecules to move because of the current, leading to a line becoming short or open. So there is a move to refractory materials like ruthenium or cobalt, especially at the lower layers, because of the fact that most of the lower layers with copper anyway require a liner, and the lower layers tend to have much higher electron densities. Finally, current crowding at the contacts of the transistors also leads to an effective resistance. So when you talk about resistance by itself, it is not as simple as just the sheet row. There are a lot of other parameters that do impact the resistance of the wire in the chip. Now again, most PDKs will release a sheet row for various layers. So once you know sheet row, we normally model the resistance as rho SH by W, and it's modeled as some resistance per unit length of the wire. Again, because of the fact that the resistance of the wires keep reducing as you go to higher and higher metals, we normally use the top level metals when we want to route fast signals. Now, another problem occurs with high frequency is that at high frequency, because of the inductive effects associated with this conductor in a dielectric medium, the current in the conductor tends to only conduct along the surface of the metal due to electromagnetics. And so what happens is that as the frequency of the signal increases, the cross section of current is no longer uniform. Most of the current is flowing at the outside, or most of the current flows in the outer part of the cross section, and this distribution in current density is a function of the frequency. Now this effect is known as a skin effect, and it's associated with the skin depth, which is roughly related to the resistance of the wire and the permittivity. The skin depth is related to the resistance of the wire and the permeability of the dielectric and the frequency of operation of the particular signal. And so if I assume that the current is only carried by a delta thickness around the width of the wire or around the circumference of the wire, that means that the resistance of the wire is now grossly underestimated if I assume that the current flows all through the wire. So the resistance of the wire actually increases as a function of frequency. So what happens now is that in addition to the resistance increasing, which itself is a problem, the resistance also becomes a function of frequency, which means that it starts to create distortion in the signal. This again it's a prominent issue when you're dealing with wide wires, because those are the ones generally used to carry large or fast signals, and on the wide wire skin effect is prominent. Now if you talk about the third parameter, which is inductance, and it has become consequent in the last 10-20 years because of the fact that you're using much higher frequencies for the various signals on the chip, and the consequences of the inductance being a factor in the interconnect. So the inductance causes ringing and overshoot effects. It also ends up creating reflections of signals due to impedance mismatch, which ends up losing the amplitude of signals. Inductive coupling can also be created between adjacent lines, leading to noise and mismatch. And switching noise can also occur due to LDI by dt drops across lines. Right? So these become additional noise sources in the circuit. So now let's talk about the models. So the models again are dependent on how you want to trade off the ease of estimating the performance of interconnects versus what is happening in reality. So if you think about the models, the simplest model of an interconnect would be that of an ideal wire. That is, you have 2 points A and B, and the wire is an inconsequential connection between A and B. That is, it has no impact on the electrical behavior, and the voltage at one end is immediately propagated to the other end of the wire with absolutely no measurable delay between the two. Or in other words, the entire wire is essentially equipotential. Now the other model is what is known as a lumped model. So we normally use that when only one of the parasitics is important, say the capacitance, and when the interaction between the components is very small. So when the resistive component of the wire is small, for example, and the switching frequencies that you're using are in the low to mid range, then we can essentially model the wire as just a capacitance. And in that case, what's going to happen is the wire still remains an equipotential region. However, and the wire by itself will not induce a delay in the system. But what the wire does is the wire loads the driver, and hence it will impact the performance of whatever is connected prior to the wire. So this additional capacitive load is going to slow down this gate. Now, when resistance also becomes important, the wire can be thought of as a resistance and a capacitance together. Now, what happens is we'll look at it shortly that this model tends to overestimate the impact of the resistance. That is, you see that an R and a C, if I just model a long wire which is one resistance and one capacitance, it tends to overestimate the delay. So what we do is we typically model the wire as a distributed network. That is, the wire can be thought of as multiple chunks of R's and C's connected in series to each other. So here I've broken a wire from an input voltage to an output voltage in terms of n chunks of an R and C, where each resistance can be thought of as the resistance of the wire over the small bit. So if I use Elmore delay to calculate the delay between B in and B out, then essentially my Elmore delay can be given as sigma I to 1 to n of Ci times Rin, right? And so at every node I, the effective resistance to Ci is going to be just the sum of all the resistors till that particular node, right? Because here you have a very simple RC tree with no branching whatsoever. So in other words, I can write my delay as C1 R1 plus C2 into R1 plus R2 plus C3 into R1 plus R2 plus R3, so on and so forth, times Cn into the sum of all the resistances connected prior to Cn. Or in other words, if I assume that I have a wire of length L that is broken into capital N segments, let's call small r and small c to be the resistance and capacitance per unit length of this wire. Then each resistance here is equal and is equal to small r times L divided by N. Right? Small r times L is the net resistance of the wire. It's broken into N segments, so each segment has a resistance of RL upon N. Each segment has a capacitance of CL upon N. So now if I plug these two back into the previous model, what I get is my delay from input to output or across the wire can be thought of as an arithmetic progression of CL into RL by N squared. So I can write this as RC L by N the whole squared into N plus 1 by 2, the sum of the first N integers. Now as N tends to infinity, that is when I make this model truly distributed, what happens is that this delay of the wire converges to RC upon 2 into L squared. Or in other words, it converges to the R wire times C wire by 2. Right? So you see that the delay of this wire, if you use a distributed network which is close to reality, is actually not the RC delay, but rather half of the RC delay if it assumed the wire has a single resistance and a single capacitance. So hence this model is a better model than using just a lumped resistance and a lumped capacitor. Now two things to note is, one is that the delay of the wire is quadratic to length. So which means that as you make your wires longer, the impact on the delay is not linear but quadratic. So it becomes harder and harder to work with longer wires. And secondly, the delay of the distributed line is half the delay that would have been predicted by the lumped model. Hence, almost always we never use the lumped model because it is overestimating the delay of a given line. To solve accurately, right, we can also use differential equations, right? So let's think about an infinitesimally small section of the wire, which can be broken up into three values of voltage, an I minus 1, an I and an I plus 1, with a resistance R delta L at each segment and a capacitance C delta L present at the node. Now if I set up the difference equation on this line by setting up KVL at this point, what I get is that when I make these delta L's infinitesimally small, I get that RC dou V by dou T is equal to dou squared V by dou X squared. So what I get is the wave, something similar to the wave propagation equation. Or what I see is that this equation is essentially transcendental. It has no closed form solution. And so approximate solutions invoking the ERF function exist for this equation. And so the key to remember is driving these RC lines is not trivial. And the impact of these RC lines on the delay and the fact that these lines can cause signal degradation is one of the trickiest problems that one needs to solve with respect to timing on a chip. So the question is, how do you choose the right model for the interconnect? So one rule of thumb could be that make sure that you include the RC delays of the wire only when the RC delay of the wire is comparable or longer than the gate delay. So which means that suppose you have a very short wire whose delay is much smaller than the gate delay, you're fine to ignore the delay of the wire. But in case the wire delay is of the same order or larger than the gate delay, then definitely you're going to grossly underestimate your delay if you do not include the delays of the wires. So typically we talk about a critical length of a line above which the RC delay must be considered. So one particular approximation that could be used is something similar to this, where we say that the critical length of the line is given by the square root of the gate delay divided by 0.38 RC, where R and C denote the resistance and capacitance per unit length of the line. So you see that this critical length depends on which gate is driving or the size of the gate that is driving the line, as well as the interconnect resistance and capacitance. Right? So depending on which layer among the 12 or 15 layers you're using for the signal, the critical length is going to change depending on the material used. So RC delay should be considered when the rise and fall times of the signal are much less than the RC delays, right? So this is also further going to delay the signal. So if you ignore the interconnect component, then you're going to again underestimate your delay in your line. So two models can be used to model the interconnect delay. They are known as the T model and the pi model. So we either distribute the capacitance at the input and the output of the wire, or distribute the resistance between the input and the output. Now both of these give the delay to be roughly RWCW by 2, so they are much better than the lumped model that we had thought of earlier. Now when switching speeds become very fast and you have to actually consider the inductance of the wire, then what happens is that the interconnect line begins to look like a transmission line. In other words, the signal propagates over the medium just like a wave would. So you can think of the wire as essentially consistent of a resistance, an inductance, a leakage path to ground, and the capacitance of the wire. Now if I assume that this wire is sitting in an ideal dielectric, which means that the leakage to the ground is 0, then I can again write a distributed model for the KCL KVL within this section of the wire, And what you get is that the voltage you get is controlled by this equation where dou squared V by dou x squared is RC dou V upon dt plus LC dou squared V by dou t squared, which looks like the wave propagation equation. So again, if I assume that this is a lossless transmission line, right? So here I'm trying to induce what the impact would be. So if I assume that the resistance is negligible, because remember normally inductances kick in for the top layer metals where the resistance, unless you're working at very high frequencies, is not high. What you end up getting is you end up getting an equation of the transmission line here. Or in other words, if I give a step input to this line, the step input is going to propagate with the velocity which is given by 1 by square root of LC. Or in other words, the speed of light which is divided by the product of the permeability and the dielectric constant of the dielectric. And the propagation delay of the wire is roughly the square root of LC. Now at any point in the wire, if I were going to look at the input impedance of the wire, the input impedance is going to be given by this term, square root of L upon C. What we see is that the impedance of the wire is only material dependent and is independent of the length of the wire. So this is very important because any line of arbitrary length has a constant impedance. So designing a driver at these cases generally tends to be easier. Now, in a transmission line, the behavior of the transmission line is strongly influenced by its termination, because now instead of thinking of the signal as a voltage or a current, you're thinking of a signal as a wave that can be reflected back. And so if I think about the resistance, terminal resistance as some R, then I can talk about a reflection coefficient, which is nothing but the ratio of the reflected voltage to the incident voltage, which can be given as R minus Z naught upon R plus Z naught. So I can think about three cases. In the case when I have impedance matching, that is when I terminate the wire in such a way that its resistance is the same as the input impedance of the wire, then essentially the wire does not see a termination. The termination appears to be a continuous extension of the wire, and so there is no loss of signal at that point. Suppose my terminal resistance is infinite. If I have a very large resistance connected, then essentially I have rho is equal to 1, in which case my reflected voltage is the same as the incident voltage. So in this case, I'm going to see ringing in my signal. So my output voltage is going to shoot up and then eventually settle down. On the other hand, if I have an open circuit at my termination, then essentially my reflected voltage is equal to my incident voltage. I'm not able to get output at the terminated value. So therefore, it's very critical that when you're using the impedance model, when you're using the inductance model, you need to terminate the lines appropriately so that you ensure that your R is as close to Z0 as possible to prevent any issues related to ringing or loss of signal. Now let's look at the impact of the interconnects. So the interconnect impact both the delay and the energy of the system. The delay is impacted through increased wire cap, which occur at the load of the gate, as well as long wires which have both R and C's on them. And so that long wire is going to impact the propagation delay of the entire path. Now T and pi models generally give a good approximation for the delay in long wires, and so for hand calculations we use these models to estimate the delays. Now the energy is set essentially by the wire capacitance. So when we have long wires or we have a lot of interconnect, that entire capacitance will need to switch as your signals travel across the wire, and so every time you switch those capacitances, you're going to be burning power in the system. Now another problem with capacitance in wires tends to be with crosstalk. So if I think about two wires that are sitting adjacent to each other, wire A and wire B, on different metals, say M1 and M2, then I can talk about a coupling capacitance that can exist between these two wires because they share a common area and a dielectric between them. And so basically, if I have a capacitance which I can call as an adjacent capacitance, then for a voltage difference between A and B, I can have a charge that can be associated with this adjacent capacitance, which is given by Q given to C adjacent times delta V. So where delta V is the total voltage change between layers A and B. And if I think about switching between 0 and VDD, in the worst case, this can be as high as 2 times VDD. So in other words, the impact is going to be worse when one is switching up while the other is switching down. And if you're going to be conservative in your design, you're going to assume that this is going to be in the worst case when you'll say that this wire switch in opposite direction, at which point the impact of crosstalk is going to be the maximum. So if I think about the wire as we normally talk about an aggressor and a victim. For example, when A is switching, what is the impact a switch on A will have on B, which is the victim, will be dictated by the capacitance, the coupling capacitance that exists between A and B, as well as the capacitances of B and A in seclusion. So if I talk about an delta V on the aggressor, that if I say that the aggressor has a voltage change of delta V, I want to know what is the change in the victim that I will see when the aggressor changes by, say, a few volts. So in that case, if I just look at this is given by a simple capacitive division, and I see that the delta V of victim is nothing but C adjacent divided by the total capacitance of B times the aggressor delta V, right? And so normally this ratio is going to dictate how much of the voltage is going to be coupled to the victim. And you see here that it's a function of the adjacent capacitances, right? And so if I think about a stack where I have if I separate the layers between M1 and M2, then I'm going to reduce this crosstalk. But if I separate these two layers, then I make the stack taller, which makes it hard to create vias, etc. in this layer. Now to be careful, I need to ensure that these nodes are driven, right? So normally these wires are associated with a driver resistance on both sides. So let's assume that I am driving this wire A through a driver whose resistance is given by R aggressor, and similarly B is connected to a gate whose resistance is given by R victim. Then in that case my delta V victim can be tempered by this ratio of the capacitances times 1 by 1 plus K, right? And this K is nothing but the ratios of the RC delays of the aggressor versus the victim. What you see in this case is that coupling becomes critical only when you have weakly driven nodes. That is, if you have a floating wire anywhere or a floating piece of wire somewhere, it is likely then that piece is going to see a large impact of this coupling noise. So we'll see cases of circuit design where there will be nodes which are weakly driven. So this becomes a problem only when we look at weakly driven nodes. Otherwise, if you ensure that all your nodes have a good driving gate connected to them, then this crosstalk can be largely controlled. Now, if you see that the R and C of the wire increase with L, and hence the delay of a wire increases with L squared. So a simple way to reduce this square dependence on the length would be that if we can break this wire into n stages and insert a buffer or a repeater after every small stage, right? And so the logic that goes behind it is every segment has a flight time of L by n the whole squared. And if you look at the line, this is repeated n times, so the time of flight of the line reduces to L squared by n. So I can break the square dependence on the length of the wire by breaking it down using repeaters. Now let's look at the pros and cons of the same. So for example, let's make it simple by saying that I can tolerate a true signal as well as a complement signal at the output of the wire. So a repeater can be just made using an inverter. So if the distance between these repeaters is very large, then the wire can dominate the delay of the system. And if the distance between the repeaters is very small, then the inverter delay can dominate the delay of the system. So essentially you want to find a good mix between the wire delay and the propagation delay, or you need to find an optimal between the two. So let's assume that we have a unit inverter whose resistance is R and whose gate cap is C. And if it has a parasitic delay of P inverter, then the diffusion cap is given by C times P inverter. Again, let's talk about the resistance and capacitance of the wire per unit length to be Rw and Cw, and assume that the inverter of size W is used as a repeater. So I can think of my Elmore delay model for every segment as this is the repeater that is driving the segment of the wire. So its resistance, drive resistance of the gate is given by R by W because the inverter is size W. Similarly, the capacitance is given by Cp inverter into W. Here I have used the pi model of the wire. So I have the capacitance broken into two and this resistance. And then here I have the total capacitance of the next repeater, right? So this would be one segment from one repeater to the next repeater. So if I look at the delay of this line, I'm going to do this n times. So I can give the total propagation delay of the wire in this format, right? And so here you see that the total propagation delay depends on the driver resistance as well as on the wire resistance and the inverter delay. And so this function, if you want to design for repeaters, you want to minimize this function for n, right? So if you minimize this function for n and w, you want so that you only introduce minimum number of repeaters and ensure that the size of the repeaters is not very large, so keep the area under control. So this function can be minimized and you can propose a design that uses the optimal number of repeaters so as to minimize the delay. So when you minimize that function, what you get is that the optimal L by N is given by this ratio, and for such a ratio the delay of the wire per unit length is given in this format, and which means that to achieve this delay the inverter might use an NMOS whose width is given by this ratio of square root of R by C into CW by RW. So it's related to the drive properties of the repeater as well as the properties of the wire. And if you think about the energy per unit length that is required to send a bit, it is given by this. So it is proportional to the number of segments that we have in the wire. So what are the drawbacks of repeaters? So repeaters may sound very interesting and may sound very usable, and obviously they are in special cases, but to keep in mind that there are a lot of drawbacks associated with repeaters. Primarily, it complicates design since you need to use an even number of inverters, or you need to adapt your design so that the design can accept both true and complement inputs at the end of the line. If I use both inverter pairs or buffers, then that's going to further increase the delay and the area associated with the repeaters. And the other problem is that generally wires using repeaters tend to be directional, right? So this having a repeater induces directionality in the wire. And so if you look at bidirectional buses or tri-state buses, those cannot be optimized using repeaters. So repeaters can be used in a very small number of cases where you have unidirectional signaling on the chip. So to conclude, interconnect delay dominates the performance of the chip, especially in critical blocks like the clock distribution network. The delay of the wire grows as a function of L squared, and you can use repeaters in long wires to reduce this dependence on the square of the length. Typically, process technologies have 12 to 15 layers which are used for interconnection, and designers choose the interconnect wisely depending on the slack that is available for the specific data path or connection. Good modeling tools are generally available for extracting the RC delays, and so generally we use Elmore to do hand calculations and then rely a lot on these extraction tools to extract the delays of large data paths.